Hello everyone. In this week's lecture, we'll discuss about different modeling approaches in land use modeling as part of the travel demand modeling process. So the prediction of land use is one of the very important inputs to the transport modeling process. Generally, there is a high level of uncertainty in every component of the travel demand modeling process. And similarly, there is very high level of uncertainty in land use prediction. The distribution of activities also has a very fundamental impact on the tasks that need to be carried out in the transport system, while the effectiveness of the transport system can dictate the location of activities. So what it says here is there is a two-way relationship between the distribution of activities, whether it's the distribution of jobs, distribution of residential location, distribution of retail, shoppings, etc. There's a two-way relationship between the distribution of activities and the functionality or performance of the transport system. So if you change the distribution of activities, the functionality of the transport system will change. And also, if you change the functionality of the transport system, it will affect the distribution of activities. This is a very important relationship to keep in mind. Also, for any urban area and over any reasonable time frame, we expect to see some changes in population and employment. And that's actually the basic of the land use modeling. And in the context of providing inputs to a travel demand model, the purpose of a land use model is to provide a method to spatially distribute the changes to population and employment and other land uses. So the outcome of a land use model is the spatial distribution of population, employment, and other activities of interest. Here is a schematic illustration of the interaction between a land use model and a travel demand model, where on the left you see a travel demand model box, and on the right you see a box representing a land use model. So one of the first steps in land use model is calculation of accessibilities. To calculate accessibilities, as we will talk more later, you need the travel times from the travel demand model. So you get the travel times from the demand model, you input it to the accessibility calculations. Then within the land use modeling framework, you predict the changes in population, you predict the changes in employment, and then as a result, you will end up with a new distribution of population and employment for future. And that will feed back into the travel demand model, and it will change the results of the trip generation and trip distribution, for example. So you run the travel demand model again, you get new travel times, you will feed it back again to the land use model, and you continue this iterative process until you reach convergence. Population change is one of the most important part of the land use modeling. In its simplest form, population change equals to inflows minus the outflows of people. So change in population is equal to the number of birth plus number of immigration into the study area minus the number of death minus the emigration, the number of people moving out of the study area. Many factors can influence population change. The birth rate can be affected by the age structure of the population. For example, if a country is aging, it will affect the birth rate. While the economy can also have an effect on birth, immigration, and emigration rates. Government policies have a direct impact on immigration, which as a result could affect the economy, which is the case in Australia. Employment change is the second most important part in land use modeling. Changes in employment are often driven largely by the economy, although some sectors like retail, shopping, and service providers are more related to the overall population than the economy. So for transport studies, the type of employment is as important as the number of people employed. For example, a large shift from manufacturing to service industries may result in little change in the number of people employed, but will have a significant impact on where these people will work. So retail, shoppings are usually distributed among residential areas within the city boundaries. However, manufacturing industries are often located in the fringe of the city where residential densities are low. There are different types of models of land use. We have macroscopic models of land use and microscopic models. Within the macroscopic category, we have regression models, we have Hansen's accessibility model, and Lowry's model, which we will talk about. And as part of the microscopic models, we also have land use utility-based models, which again borrow some ideas from the discrete choice modeling and look at the land use modeling framework as a discrete choice modeling process to predict the location of the new residential, location of the new employment activities, and etc. Here's an example of a land use model given by a very classical study by Blunden and Black, derived from a real town in the United States back in 1966. This is just an example to show you how a regression-based land use model may look like. So here, what we try to predict is the y variable, which is the growth in the dwelling units per unit of vacant land. It basically tries to predict the number of growth in the number of dwellings per area as a function of different factors, including the zoning protection level. For example, if zone that changes between 0 and 9, high values indicate a zoning aimed at preserving a residential character, and low values indicating no zoning protection. Another interesting factor in this model is the percentage of the total land in residential use. The model also includes the accessibility to employment, dwelling unit density, and percentage of total land in industrial use. Interestingly, what you see in this land use model is there is very little factor representing the characteristics or the level of service of the transportation system, except this accessibility to employment. Speaking of accessibility, we can define accessibility generally as the desirability of an area. So again, according to the classical study of Blunden and Black in 1984, accessibility is the concept that links the spatial location of land use activities with the service provided by the transport system. It is the close proximity of activities plus well-developed transport that makes the internal structures of cities accessible. Accessibility describes how convenient land use activities are located in relation to any specified zone, and how easy or difficult it is to reach the activities via the transport system. So the basic concept in accessibility is that the accessibility of a particular zone, the accessibility to a particular zone, increases with the number of activities within that zone. For example, if you're looking at job accessibility, if you increase the number of jobs within a zone, you increase the accessibility to that zone. Also, it decreases as travel time or distance increases. So if the distance or travel time to a specific zone increases, the accessibility decreases. So this relationship is very similar to the gravity model, which we've used previously in the classical four-step travel demand model to determine the number of trips between origin and destinations. To measure accessibility, we usually define an accessibility index, which can be mathematically expressed as AII, which is the accessibility of zone I, is equal to the summation of the number of activities in zone J multiplied by a function of travel time, something like a deterrence function as we worked before. And this function of travel time usually have either a negative power formulation or a negative exponential formulation. So in Hansen's accessibility model, which was first developed in 1950s and 1960s, we look at accessibility to employment opportunities as a major determinant in allocating population growth. So in Hansen's model, the accessibility between zones, zone I and zone J, is calculated by dividing the number of jobs by the travel time between the zones. So we can express that mathematically as the accessibility index of zone I is the summation of the number of jobs E in zone J over a function of travel time, which is usually a power function of travel Tij. And usually we use power equal to 1, but this could also change. And then after we calculate this accessibility index, we assume that the overall growth for an entire region is known, and the share of the growth for every specific zone is then calculated by a simple formula that GI represents the population growth in zone I is equal to the population growth of the entire region multiplied by a ratio, which is the ratio of the accessibility index of zone I, which is similar to the zone that we are trying to calculate the population growth for, power x, again this is an experimentally determined exponent, multiplied by the number of new jobs in zone I. VI here represents the number of or new employment growth opportunities over the summation of the accessibility index of J power x multiplied by Vj over all the zones in the network. It is a good time to look at activity 8.1 to work with an example of Hansen's accessibility model. In this activity, we focus on a simple three-zone city, as you can see here, zone 1, zone 2, and zone 3. The distribution of employment and development opportunities are given in table 1, while the travel times are shown in table 2. So we have zone 1, zone 2, and zone 3. We have the number of jobs in each zone, and we have this development opportunities, which basically represent the number of new jobs that will be available in those zones in future. So for example, zone 1 has 20,000 number of jobs, and it will have 1 additional 1,000 jobs in future. If you look at zone 3, it currently has 4,000 jobs, but in future it will have 10,000 additional jobs. And the travel time matrix is also given. Here we are assuming alpha equal to 1. If you remember from the Hansen's accessibility model, the problem is asking you to calculate the accessibility index using the Hansen's model. So to calculate the accessibility model, we use the formulation given in the slides, which the accessibility index of zone I is equal to the summation over all the zones of the number of jobs in zone J over the travel time of ij power alpha. Alpha is equal to 1, so we just ignore that, it's Tij. So therefore, you can calculate an accessibility index for every zone. Accessibility index of zone 1 is equal to the number of jobs in zone 1, which is 2,000, over the travel time of 1, the internal travel time of zone 1, plus 10,000 jobs over the travel time between zone 1 and 2, plus 4,000 jobs over the travel time between zone 1 and 3, which ends up to 4,913. You can calculate the similar accessibility index for zone 2 and zone 3 using the information given in table 1 and table 2. In the second part of the problem, we're assuming that 2,000 additional people need to be accommodated in the city. So the population growth of the entire city is assumed to be 2,000. Now we would like to predict the growth in population in every zone, assuming that exponent is, in the Hansen's model, is 2. So coming back to the solutions here, if you remember the population growth formula, we had the population growth of zone I is equal to the population growth of the entire region multiplied by a ratio, which is the accessibility index of zone I power 2, this x equal to is given by the problem, multiplied by VI, which is the number of additional jobs in each zone, over the summation of the same multiplication over the entire zones in the city. So as a result, we can calculate, we already have the accessibility index of the zones calculated from the previous part in the problem. The number of additional jobs VI is given by the problem. So we can start calculating this term here, AI power 2 multiplied by VI for the rest of the calculation. So we calculate this and we calculate the summation, which is the denominator of this ratio. And then now we can start calculating the GI for every zone, G1, G2, and G3. So G1 would be equal to GT, which is the total population growth of the entire city, which is 2,000, multiplied by the ratio of 2.41 over the summation 7.35, which gives you 656. If you calculate the same thing for G2 and G3, you end up with numbers 773 and 571. So this is the new population growth distribution in the city. This means zone 1 will have 650 plus people living in it, in addition to the existing number of residents. G2 will have an additional 770 people, and G3 will have an additional 575 people living in the zone. Going back to the problem, in the part C, the question is asking us to investigate the impact of an investment in the transport system, which would reduce the travel times to and from zone 3 by 10 minutes. So the travel times from and to zone 3 will reduce by 10 minutes. What impact will this have on the additional population allocated to each zone? So what we will do, we will decrease these travel times to 40 and 30. So here is the new travel time matrix, where we have 40 and 30 minutes, 40 and 30 minutes here as well, but the internal travel time of zone 3 doesn't change. Now we need to recalculate the accessibility indices because the travel times are changed. Using the Hansen's accessibility index formulation, which was the number of jobs over the travel time, plus the number of jobs over the travel time, plus the number of jobs over the travel time, for every j, you can calculate the new accessibility index. We do the same thing for accessibility index of zone 2, accessibility index of zone 3. Now again, to calculate the population growth in every zone, we need to recalculate the term AI multiply VI. Now we use the new values of accessibility index, the new values of jobs for the scenario that we are trying to evaluate, and we calculate new terms as provided here. Now we need to substitute all these new values in the population growth equations. So the new population growth of zone 1 would be 2,000. That's the total population growth of the entire city. Multiply this ratio of the AIV over the summation of the AIV. So this means the new population growth in zone 1 would be 608. In zone 2, 723 more people will live, and in zone 3, 669 people will live. So now if you compare the base case and the scenario we just tested, you can actually see the differences in the population growth just as a result of reduction of the travel time between zone 3 and all the other zones. The other model that we're going over is the low-rise accessibility model, which is a refinement of Hansen's accessibility model. In the Hansen's model, we did not recognize different types of employment, but in the low-rise model, the advantage is that we break down the employment into two types, namely basic employment and service employment. What is basic employment and service employment? Basic employment is defined as those type of jobs or industries whose existence is governed by factors outside the model, while service industries locate to serve the residential population. So basic industries are generally interpreted as those that are export-oriented in nature, which provide the economic impetus for development and the reason for the existence of the urban region. The low-rise accessibility model includes three basic equations. The first one is P equal EA, where P is a vector of population in every zone, while E is a vector for total employment in a zone, and A is a zone-to-zone matrix of work-to-house journey accessibility. The second equation is ES, which is the number of jobs, number of service jobs is equal to the population multiplied by B. What is B? B is a zone-to-zone accessibility matrix related to household to service jobs journeys. And finally, the last equation is the total employment is equal to the basic employment plus service employment. Low-rise model is an iterative process. You start with basic employment of zones, then you estimate the residential location for basic employees, then you calculate the population associated with basic employees. In the next step, you focus on service workers. Then again, you calculate residential location of non-basic employees, and then you continue this process until you reach convergence. To better understand the low-res model, let's go over activity 8.2 together. So in this activity, we assume a 4-zone city with the following basic employment vector as given. We have 4 zones, so the number of basic jobs would be 100, 150, 120, and 80 in every zone, in each zone. A and B, as you saw in the slides, are zone-to-zone matrices of workplace to household and household to service jobs accessibility matrices. You can calculate this accessibility matrix following the equations that we saw in the slides before looking at the Hansen's accessibility. So the journey to home matrix of accessibility is calculated and is given in this problem. The journey to service jobs matrix is also provided. Here we are using the low-res model to estimate the distribution of the total employment and population in this city. We do one iteration, but I would like you to continue the iterative process to reach convergence. So we start with the first equation, which was P equal EA, where the distribution of population is equal to the employment matrix multiplied by the accessibility matrix of A, which was workplace to household journey. We start with, because we don't know the total employment matrix yet, so we start with basic employment only as it was given in the problem. So we have the employment matrix multiplied by the accessibility matrix of workplace to household, and we get the population distribution. In the second equation, we get the service jobs distribution. So ES, which is the employment of service-related jobs, is equal to the population matrix multiplied by the B accessibility matrix, which was the journey to service jobs accessibility. So the distribution of the population will be multiplied by the accessibility matrix B, so we get the distribution of the service jobs in the city. In the last equation, we now estimate the total jobs, which is service jobs plus basic jobs. We already had the basic jobs given by the problem. We estimated the service jobs and we get the new distribution of the total employment. Now that we have this total employment calculated, we can go back to the first equation and replace this E, which we first assumed only as basic jobs. We replace this employment matrix by the new employment vector that we have calculated, and we continue the iteration. And then we keep doing that until we reach convergence. Other type of land use models are utility-based or discrete choice modeling-based land use models, which takes into account different factors and characteristics to derive a utility function that describes possible alternative and assign probabilities on the basis of this function. This is very similar to the discrete choice modeling topic we discussed before, the mode choice, the route choice. Here in the land use modeling perspective, we estimate different utility-based discrete choice models for residential choice model or employment choice models. So you define a utility function. I here is your beta, as you remember from the discrete choice modeling lecture, is the beta in the utility function that needs to be estimated. And S is the attributes of the alternatives, basically. Here we are rewording the definition of them a little bit, where I is defined as the importance of characteristic I to location seeker K, and SIKJ is the satisfaction with characteristic I in area J as perceived by location seeker K. As I said, it's basically the same as beta multiplied by the attributes of the alternative or attributes of the decision maker. So you specify a utility function, and then you calculate a probability, for example, using a logit framework, which is the exponential of the utility of the alternative over the summation of the exponential of the utilities of all the other alternative. So very similar to discrete choice modeling discussions, you can create utility-based land use models. Another popular model in land use modeling framework is car ownership models. Car ownership models are important in market research. Like vehicle manufacturers and petrol companies are very interested to predict the car ownership levels of the population. Transport modeling is also concerned with vehicle attributes like the size of the cars and etc. Also, car ownership models are important in determining the need for new infrastructure, like whether we need to build new highways, whether we need to build new parking. If the car ownership model predicts a high level of car ownership in some new suburbs, then we need some new infrastructure. So car ownership models can follow different frameworks. One of the classical car ownership models is called Quarmby and Bates model, which I call QMB model. It's a basic model which includes a few equations that I will discuss just right now. So the first equation of the QMB model looks at the ratio of the probability of having zero car over 1 minus probability of having zero car. So just to give you a better understanding, we have in this QMB model, we have P0, P1, and P2, which represents the probability of having zero car, probability of having one car, and probability of owning two and more cars. Obviously, in the last equation, you can see that the sum of the probabilities must be equal to 1. Going back to the first equation, so we look at the probability of having zero car over 1 minus probability of zero car is equal to alpha 0, alpha here is a parameter to be estimated, minus I power a parameter multiplied by D power a parameter, where I represents the annual family income in $1,000 and D is the number of residents per acre, which is basically representing the population density. Again, in this equation, P, I, and D should be provided or should be obtained from some data, and alpha, beta, and C here needs to be estimated. The second equation of the QMB model look at the ratio of the probability of having two cars over the probability of having one car, which again we will have a few other parameters to be estimated, including alpha 1, B1, and C1, but I and D remains the same as it is the income of the household and the population density. So in this equation, we will have alpha 1 multiplied by the exponential of the a parameter multiplied by income. The entire term is multiplied by the population density power a parameter. If you take the logarithm of each side of this equation, you can a little bit simplify it, where we take the logarithm of the left side of this equation, which gives us logarithm of p2 over p1. I'll talk about this term later a little bit, that where this term comes from, but it is s, which is a constant, multiply 1 minus probability of 0 car minus probability of 2 car, which is equal to this p1. I'll talk about this in the next slide. But the right side of the equation 2 will be transformed when we take the logarithm. It will be transferred to logarithm of alpha 1 minus this beta comes out of the exponential, and logarithm of exponential is the actual variable inside the exponential, so we will have minus b1 income. And then when you take the logarithm of a term like this with the power, this power comes out behind the logarithm, and we will therefore have minus C1 logarithm of the population density. Again, there's no need to memorize these formulations. If someday you needed to calculate car ownership probabilities, you can always come back, have a look at these equations, and try to estimate them. So let's go and talk about this probability of 1 car, 0 car, and 2 car, and how this term here, s multiply 1 minus p1 minus p2 is equal to actually p1. So to better understand these equations, here we have a visual illustration of these p1, p2, and p3. P0, p1, and p2, where we represent them as functions and curves as a function of income. So have a look at this curve, which represents the probability of having zero car. The probability of having zero car will decrease as the income of the household increases. And that makes sense. If you're earning more money, you're more likely to have more cars. The probability of you remaining a zero car household will actually go down. Probability of having one car actually has an interesting pattern, whereas the income of the household increases, the probability of buying one car and moving from zero car to one car increases, but after a certain point, if the income increases, the probability of remaining a one car household actually goes down because you're more likely now to have two or more cars. Now, if you look at the probability of having two or more cars, has a very clear pattern that as the income of the household increases, the probability of having two or more car increases. But there is a cap, which is represented by that constant s, which put a cap on the probability of owning two or more cars. But where does this s come from? It could come from the percentage of the population in your sample that actually have two or more cars. To better understand how we can actually estimate a QMB model in a car ownership example, let's have a look at activity 8.3. So in this activity, we are considering the data as given in this table, and we assume a cap of 78% for S. The problem wants us to estimate the parameters of the QMB model for a fixed residential density value. So what we're given is, for every income category, for different income levels, we are given the probability of owning 0 car, 1 car, or 2 car. So what we need to do is we need to formulate the QMB model and start estimating the parameters inside these formulations. So let's start with the first equation of the QMB model, where we have the probability of 0 car over minus 1 minus probability of 0 car equal to alpha minus I and multiply by d. So if we take the logarithm of this equation, both the left side and the right side of the equation, we end up with the logarithm of the p0 over 1 minus p0. When you take the logarithm of the right side, you'll end up with logarithm of alpha 0 minus this b comes in the back, so we will have minus b logarithm of I. But the problem is assuming that the residential density value is fixed. So we need to have this d power c equal to 1. How can we make this d equal to 1? To get rid of it, it just requires us to assume c is equal to 0. Whatever power 0 is equal to 1. So we assume c is equal to 0, so this entire d power c will be equal to 1, and we don't need to worry about it anymore. So we have this logarithm alpha minus b0 logarithm of I, which was the household income. What does this equation look like? It actually looks like a simple linear regression. If you consider the entire left side term as your y, your logarithm of income is your x, so this b is the coefficient of the regression, and this logarithm of alpha is a constant in the regression. So we can actually form a linear regression here to estimate this alpha 0 and beta 0. So I've actually done that in an Excel file. So here I have the probabilities of 0 car, 1 car, and 2 car for different income levels as given in the problem. I then, for every income level, I calculate the ratio of P0 over 1 minus P0, which I needed for the first equation. I also calculate P2 over P1, which I needed for the second equation, which we will cover in a minute. So from there, to actually estimate the left side of this equation, which is my y value in the linear regression, I need to take the logarithm of p0 over 1 minus p0. So here I'm looking at the logarithm of P0 over 1 minus P0, and I calculate that. I also calculate the logarithm of income. And then if I plot them against each other, I can fit a nice linear regression and estimate the parameters, where the coefficient behind this x is my beta 0, and the constant that is estimated is the logarithm of alpha 0, which if I take the exponential of it, I will get the actual alpha 0. Going back to the problem, so far we have estimated this alpha 0 and b0. Next, I'm going to use the second equation, the simplified or the transformed version of the second equation, to estimate alpha 1 when beta 1. Again, here C1 we assume to be equal to 0 because of the fixed residential density value. So this entire term C1 log D will be 0, so we don't have to worry about it. So we write down the equation again, and when you look at it, similar to the previous one, it looks like a linear regression where the entire term on the left side of the equation is your y, your income is your x, and beta is the coefficient in the regression, and log alpha is the constant in the linear regression. So we can actually form another linear regression with this. Going back to the Excel sheet, I have my income. I have calculated this logarithm of P2 over S1 minus P0 minus P2. All the equations are in the cells if you want to have a look at it later. And I can actually plot them against each other and fit a nice linear regression. And then, similar to previously, I can calculate the coefficients beta 1 and alpha 1 from this linear regression, where the coefficient behind x is my beta 1, and the constant that is estimated is the logarithm of alpha 1. If I take the exponential of it, I will end up with the actual value of alpha 1. And that's how we can actually estimate a QMB model. I would like to finish the lecture by showing you a real study of car ownership using utility-based framework, the discrete choice modeling framework. So this is a report which I will provide you with the link later, and you can have a look on your time. But going through it very quickly to show you the utility functions that is being estimated and how the discrete choice models are estimated in a real car ownership modeling framework. Here is the same utility specification as we talked about. They're using a multinomial logit framework. In the specification model, this is actually their utility specification, where they're considering different variables, including the alternative specific constant, income, HS is household size, CLD is the number of children in the household, DRI is the number of licensed drivers, EDU is the education level of household, LOC represents the household location, HD represents the household density at the block level, RNT represent the percentage of renter occupied housing, and you can see you can specify a utility function as complicated as this one. And then using BioGym or any other software, you can start estimating these coefficients, and then when you estimate the coefficient, you can start calculating the probabilities and forecasting of the number of households that have 0 car, number of households that have 1 vehicle, and so on and so forth.